Hello guys, and welcome to lecture number 6 in our series of geometrical and physical optics lectures. In this lecture we are continuing our exploration of an important phenomenon that pertains to light, and that is interference and diffraction. In the previous lecture we learned a little bit about the diffraction, and here we're going to take one step further and look at a few different concepts that are important to be studied and analyzed in order to fully understand diffraction. So we are going to describe a single slit diffraction. We will see how we can calculate the positions of the minima and maxima in the diffraction pattern. We'll see what kind of diffraction pattern is created by the pinhole versus a single slit versus rectangular aperture. We're also going to introduce diffraction grating, which represents an interesting diffraction filter very often used in photonics. An important theoretical concept that needs to be briefly analyzed and introduced is the difference between two different types of diffraction, one being so-called far field or Fraunhofer diffraction, another one being a near field or Fresnel diffraction. And then finally, at the end of this lecture, we're going to be talking a little bit about the polarization. We'll see what the polarization is, how it can be analyzed, how we can predict polarization using so-called law of Malus. And finally, we're going to be looking at a few different polarizing filters that have found many different applications in real life. As we already elaborated in the previous lecture, we said that diffraction occurs when light passes through small openings or around obstacles, sharp edges, etc. On this slide you can see three different setups that create the diffraction pattern. On the left hand side we have a small aperture of a size that's comparable to the wavelength of the light, and on the back screen, after the light passes through this small circular aperture or so-called pinhole, you can see a very unique diffraction pattern that consists of so-called airy disk as well as multiple annular rings that are positioned around the airy disk. On the picture in the middle of the slide is the case of a single slit diffraction. So here we have a single vertical slit whose width is comparable to the wavelength of the light, and if you look at the screen in the back, you're also going to see a very distinct diffraction pattern that consists of multiple maxima and minima positioned along the horizontal axis. So in other words, the vertical slit is going to produce horizontal diffraction pattern and vice versa. If you have horizontal vertical slit, that horizontal vertical slit is going to create diffraction pattern in a vertical direction. And then finally, on the picture on the right hand side, we have so-called straight edge diffraction. Here we are talking about light hitting a sharp edge. It can be edge of a knife or similar, creating a very distinct diffraction pattern that also consists of multiple bright lights that are separated by the dark lines. So before we move on to analysis of different types of diffraction patterns created by different obstacles, we also want to introduce the concept of the far field and near field diffraction. Far field diffraction is also known as Fraunhofer diffraction, and then near field diffraction is known as a Fresnel diffraction. What you can see here is a lab setup that will be used in our labs to create diffraction patterns. On the left hand side you see the source of light of a specific wavelength, and then in the middle we have specific type of a diffraction aperture. This can be a pinhole or vertical slit or diffraction grating, and then over on the other side we have a screen on which we're going to be observing our diffraction pattern. It turns out that diffraction pattern will have certain distinct features based on how close or how far is this screen in the back is to the diffraction aperture. So in order to create so-called far field or Fraunhofer diffraction, which is going to be of interest for us, the back screen has to be at a specific minimum distance away from the diffraction aperture. And that minimum distance is defined by the formula that you're seeing on the bottom of this slide. So the entire space is going to be split into two areas, so-called near field, where we can observe Fresnel diffraction, and then the far field at a farther distance, where we are going to be observing Fraunhofer diffraction. So it's important to mention that of interest for us is a Fraunhofer diffraction. So everything what you're going to be seeing on the slides that follow pertains to the Fraunhofer diffraction from a specific type of a diffraction aperture. In other words, everything that we're going to be analyzing on the slides that follow satisfies the condition shown here in a formula in a box on the bottom of this slide. So in other words, the Fraunhofer diffraction or far field diffraction is going to depend on the area of the aperture opening. So you would want to look at the opening on your diffraction aperture as well as the wavelength of the incident light. So those would be the two important parameters that are going to define how far away from the diffraction aperture is Fraunhofer diffraction going to appear. And that's the condition that we would want to make sure is satisfied if you are doing any kind of lab measurements where you're going to be positioning diffraction aperture, light source, and finally screen in the back. So here's an example. A photonics technician has been asked to produce a Fraunhofer diffraction pattern formed using light from a helium-neon laser at a wavelength of 633 nanometers that passes through the pinhole type of a diffraction aperture. The pinhole size is 150 micrometers in diameter. This photonics technician, Minati, has to set up the correct geometry for the Fraunhofer diffraction. In other words, has to position the screen in the back at a specific distance, minimum distance, at which Fraunhofer diffraction is going to appear. So you would want to use the formula on the previous slide to come up with a value of a minimum z prime, where the z prime represents the distance between the diffraction aperture and the screen in the back. Here we are analyzing a specific type of a diffraction pattern that's been produced by the single slit. So there's certain math behind this whole analysis that you would want to fully understand in order to be able to predict at what distance or at what position the bright and dark spots are going to appear in this type of experiment. So again, we're dealing with a single slit type of a diffraction aperture, and we know that in the case of a single slit, we are going to have a very distinct diffraction pattern that's going to be consisting of a maxima or bright spots and a minima or dark spots. And using this math that you're seeing here, you want to predict the position of both. So on the left-hand side, we have a plane wave with a planar wave front. And then here we have a single slit of a width small b. And then at a certain distance away from the slit is the back screen. This distance is labeled here as capital L. And this capital L distance have to satisfy the condition for the Fraunhofer diffraction as introduced on the previous slide. Now, what you can see here on the back screen is this type of a repetitive behavior. Wherever you have a peak in this curve, that's basically where your bright spot is going to appear. It's also shown here on the right-hand side. You can see the peaks. What can be observed is that the first peak is appearing exactly on the axis relative to the slit. And then we have the first order dark spot, and then here we have followed with a bright spot, and again dark spot and bright spot, etc. So the question is, at what distances away from this center spot or from the axis would the first or second bright spot as well as first or second or third dark spot are going to appear? There is a formula given here, and you can see the formula here is basically indicating at what distance would dark spots appear. So in this formula we have on the left-hand side quantity y that represents the distance of a specific dark spot from the axis of the lab setup. And then on the right hand side we have three quantities. We have a lambda that represents the wavelength of a light used in the experiment. Capital L is our distance between the diffraction aperture and the back screen. Small b represents the width of the slit. And finally, m represents an integer number that corresponds to a specific order of the dark spot. So the first order dark spot is the first one, the closest to the center of the or axis of the experiment. So for that one, you're going to take m equal to 1. So this formula is going to change into lambda L over b. And then if you want to figure out the distance of the second order dark spot from the center of the experiment, you would want to take m equal to 2 and then plug in the other values, the other quantities into the formula and calculate y2. So that's basically how this formula works and how you can predict the position of the dark spots in this experiment. As you can see, the position of the dark and bright spots in a diffraction pattern through the single slit is going to depend on wavelength or color of the light. In other words, if you are not changing anything in the setup except for the wavelength or color of light, in other words, all these dimensions stay the same, but you're just changing lambda or color of the light, the position of the bright and dark spots is going to appear at different locations. Here we have a diffraction that's been created through the circular aperture. As you can see on the left-hand side, again, we have a source, and then we have a diffraction aperture here that consists of a circular hole or so-called pinhole of a specific diameter. And then in the back, we have a screen where you can observe a very distinct type of a diffraction pattern that consists of this center disk, so-called airy disk, and then multiple annular bright rings that are separated by the dark rings. This pattern is also considered Fraunhofer diffraction pattern. In other words, the distance between the circular aperture and the screen in the back has to be at a certain minimum that's established by the formula I've introduced on previous slides. And then here we have a few formulas that can give us information about certain dimensions of these features that appear in a diffraction pattern. First, we can calculate a half-angle beam spread to the first minimum. So we have this first minimum here around the airy disk. And if you want to calculate this half angle between the axis of the system and the edge of your airy disk, formula that can be used is this first formula here, that as you can see, this half angle is a function of the wavelength of the light as well as the diameter of the circular aperture. And then based on this, we can also calculate the diameter as well as radius of the central bright disk or airy disk using the formula as shown here. Again, radius of the airy disk is going to depend on the color of light used in the experiment, is also going to depend on the distance between the circular aperture and the screen in the back, and finally also dimensions of the small pinhole or aperture on the diffraction filter. Next that we want to take a look at is Fraunhofer diffraction through a rectangular aperture. In this case here we are analyzing a small rectangular aperture that has width as well as height in order of scale of the wavelength of light. Light is coming from the left side. Again, we want to satisfy the condition of the Fraunhofer diffraction. And if all that is satisfied, we can see a very distinct diffraction pattern here that consists of bright and dark spots in the vertical direction, as well as bright and dark spots in the horizontal direction. Here we can also calculate half-angle beam divergences to the first minimum, both in the X and Y direction using the formula as given, as well as the widths of the central bright fringe in the X and Y direction. So similar to the circular aperture where we had an airy disk, in this case here we have a rectangular feature of a specific dimensions. There's specific dimension in X direction or width, as well as the dimensions in Y direction or height. Both of these can be calculated using the formula that's shown here on the bottom. We can see that the size of the central bright fringe is going to depend on the distance between the diffraction aperture and the screen, wavelength of light, as well as the dimensions of the rectangular aperture. From these three diffraction examples that we already analyzed, meaning circular aperture, vertical slit, and the rectangular aperture, you can already be noticing a specific pattern in terms of what affects the dimensions of the features in the diffraction patterns. Number one would be the color of light. Number two, the distance between the aperture and the screen in the back. And finally, number three would be dimensions of a specific aperture that's being used in an experiment. Next important concept that is related to the diffraction is a concept of a diffraction grating. Diffraction grating is shown here on the left-hand side. It's very often used in the photonics labs, and you can see here certain information that's shown on the diffraction grating. So we are talking about a specific type of a grating that consists of a whole bunch of vertical slits as shown here in the picture on the bottom. So we are not having just one single vertical slit, but many of them. And as a matter of fact, on the diffraction grating that's shown here on this slide here is actually indicated how many vertical slits are within 1 millimeter. So you can see that this specific diffraction grating that is shown here on this slide has 500 lines or 500 vertical slits within a width of 1 millimeter. You can see a few more pictures here on this slide. The picture that shows here how a diffraction is being created using diffraction gradient. You can see that the light that's coming out of this light source is basically being split in a whole bunch of beams to the phenomenon of diffraction. And then here we have a picture of what is going on if you're passing white light to the diffraction grating. We know that the position of the bright and dark spots depend on the color of a light. In other words, if you're passing red light, the bright and dark spots will be appearing at different locations than if you have, let's say, a green or blue light. So if you have a white light that consists of all the colors in the visible spectrum, those different colors in a visible spectrum that the white light consists of are going to be diffracted in the different directions, which is going to result in this breakdown of the white light into different colors and different bright and dark spots for different colors. So the position of the bright and dark spots created by the diffraction grating can also be analyzed in a similar way as in the case of a circular aperture or a single slit. So it is going to depend on the distance between the slits in a diffraction grating. So how would you predict the distance between the two neighboring slits? You would want to take the total length of 1 millimeter and divide it by 500, because there is a 500 slits in a millimeter. So that is going to be the rule that you're going to be using in the lab to figure out what is the distance between the two vertical slits. And then you can also see here that the distance between the screen on the back and diffraction grating is also going to play an important role. You can see these half angles that have been established here that would depend on the features of the diffraction grating, as well as the distance between the diffraction grating and the screen in the back. And finally, as we already mentioned, the color of light is going to also affect the position of the dark and bright spots on the screen in the back. So to conclude, diffraction grating represents an aperture that consists of thousands of slits separated by equal spacings. We already briefly talked about light being a wave, so we are talking about a wave behavior where so-called electric and magnetic field are vibrating. So electric and magnetic field in light waves vary between the positive and negative maxima in direction transverse or perpendicular to the direction of the propagation. We have introduced this concept in the previous lectures. So what you see here is specific type of a source. In this case, we are analyzing an antenna, but it doesn't have to be antenna. It can also be obviously a light source. So we have an electromagnetic wave that is propagating away from this source in a z direction. And then we also have electric and magnetic field vectors that are vibrating either in a vertical or y direction in the case of electric field, or in a x direction in the case of a magnetic field. And we can see here that the direction of vibration of the electric field and magnetic field, as well as direction of the propagation, are mutually perpendicular. They position at a right angle. This important feature of an electromagnetic wave, in which electric and magnetic field are vibrating at the directions that are perpendicular to the direction of the propagation of the light, is an important feature of so-called transverse wave. So it's important to remember that light represents an electromagnetic wave of a transverse nature. With the concept of electromagnetic field vibration in a wave of light, we are slowly introducing the concept of so-called polarization. So we are going to introduce the polarization first through this simple example that's shown here in the picture. So you can see here this guy holding a rope and then creating the waves, but by moving up and down with his hand. And as he's moving his hand up and down and holding this rope, he's going to be creating this type of a wave that you can see here that's going to be propagating in a certain direction. He can also move his hand in many different directions and create a vibration of the rope in many, many different directions. And that's what we are basically talking about when we are introducing the concept of the polarization. So the polarization basically is an important feature of light that tells us in what direction electric and magnetic field are vibrating relative to the direction of propagation of the light. So if this magic rope is just vibrating in one plane, meaning the guy is moving the hand only back and forth in a vertical direction, he's going to create so-called linear polarization. If he's moving in all possible directions, this rope, all this wave is going to be moving in all possible directions. In such a case, we are talking about an unpolarized light. So that's very important to remember. To wrap up, imagine a magic rope that you can whip up and down at one end, thereby sending a transverse whipped pulse or vibration out of along the rope. In such a case, we are talking about linear vertical polarization. And then imagine further that you can change the direction of the whipped shape quickly and randomly at your end, so that a person looking back along the rope towards you sees a vibration occurring in all possible directions, up and down, left and right, northeast, southwest. Then we are talking about so-called unpolarized wave that also exists in the case of a light. So here's the slide that explains the polarization, different types of polarizations in a little greater detail. So the case A, we can see here that if you're looking in the direction of if the wave is coming towards you, and that wave is basically represented by this dot here, you can see that in the case of unpolarized light, the electric field is basically vibrating in all possible directions. If the electric field is vibrating only in a horizontal direction, meaning the wave is coming towards you and vibrating only in the horizontal plane, we are talking about horizontally polarized light. And then if it's vibrating only in the vertical direction, such as in the case of our guy who is whipping the rope up and down in the vertical direction, in such a case we are talking about linear polarization, that's vertical. So it's important to note here that the polarization, linear polarization, can either be vertical or horizontal based on whether there is a vibration of electric field in a horizontal direction or in a vertical direction. On this slide here, we can see a short demo of a few different types of polarization. What you can see here on the left-hand side is a linear polarization. You can see that you can establish a plane in which all this red color is vibrating. So we're talking about linear polarization. In the middle, we have circular polarization. In other words, if you would stop the propagation of this wave, it would be basically operating, or it would be vibrating along the circle. You can see the tip of this red arrow that's been projected on a plane is basically moving along this blue circle. In the case of a linearly polarized wave, you can see that everything is happening along the line. So that's an important characteristic of a linear polarization. And finally, on the right-hand side, we have a so-called elliptical polarization, where the tip of the electric field is vibrating along the elliptical shape. What you see on the right-hand side is also a linearly polarized wave. Here the yellow represents electric field, and you can see that the electric field is occurring only in the vertical direction. And then the blue is the magnetic field vibration, and you can see that everything is moving in a direction from the left to the right. That's going to be the direction of the propagation of the electromagnetic wave. Polarization of the light can be controlled using so-called polarizing filters. Very often, your sunglasses, if they're polarized, are using the concept of a polarizing filter. What you can see here on the left-hand side is a polarizing filter, and you can see that the amount of light that's passing through this filter is significantly reduced. So let's now briefly explain how these polarizing filters are working. The easiest way to explain the operation of the polarizing filter is by establishing an analogy with a picket fence. We still have our guy here who is producing an unpolarized wave in all possible directions. And the question is, what is going to happen when this unpolarized wave or rope hits this picket fence here? Obviously, what's going to go over on the other side are only vibrations in a specific directions, the vertical direction. So what we have done basically here is an analogy where a polarizing filter is going to cut down all the unpolarized light and pass only a linearly polarized light in a specific direction. That's exactly why the light is significantly reduced when the light passes through this polarizing filter. So the light that's coming from the sun is unpolarized, and this polarizing filter here acts as a picket fence whereby it is going to pass only one direction. What is going to come to our eye is going to be linearly polarized light in a specific direction, while all other directions are going to be blocked by this polarizing filter. So here's a few applications of the polarizing filters. As already mentioned, sunglasses very often are using polarizing filter concept. Sometimes we're going to use 3D movies where we have a polarizing glasses. And finally, an interesting example is shown here on the left-hand side bottom. It's related to the glare or reflection of the light. It turns out that when the light gets reflected, it turns into the polarized light. So if you have a sun producing unpolarized light, that unpolarized light, after it hits the surface of the road or even the surface of the ocean, is going to get reflected as a polarized light. So if you are using polarized sunglasses, you can actually find an angle at which all that glare is going to be completely reduced or completely shut down. Because your polarized glasses are going to be cutting down the polarized reflected light as well. In this 6th lecture in our series of lectures, we have introduced a few important concepts that are related to the diffraction and polarization. We talked about the difference between the Fresnel and Fraunhofer diffraction. We have given a formula that defines the position of the Fraunhofer or far field diffraction. Then we analyzed a few different types of diffraction patterns produced through a pinhole, a slit, rectangular aperture, and finally diffraction grating. We talked a little bit about diffraction grating, what are important properties of the diffraction grating, and finally, in the second half of the lecture, we introduced the concept of polarization, electromagnetic wave vibration in specific directions, and then we looked at a few different types of polarizing filters and their applications in real life.